Chapter 24 centers on NoSQL database technologies and big data storage systems. As an introduction, there is NoSQL. Some argue that it stands for not only SQL. The problem with it is typically it's not named that way. It's typically capital N, lowercase o. So it originated from organizations that did not want to have the restrictions of a highly structured schema and schema on design, not schema on read. As such, they came up with an approach to disparage SQL. The problem was over time they started finding that SQL support was important to their business models, so they included SQL support, so hence the name became very problematic. Some attempts were made to rebrand it essentially as what you see on the screen with not only SQL. That's founded in fiction, not fact. The reality is systems that traditionally were NoSQL oriented are now supporting SQL, and SQL systems also have included many of the capabilities and capacities and characteristics of NoSQL database systems, so the line has become very blurred. The basic idea, though, is that it's focused on semi-structured or unstructured data with a high performance, generally speaking, through some form of distribution around availability and data replication and scalability. Continuing the introduction of NoSQL systems, they focus typically on things related to big data. The typical types of applications that use NoSQL include things like social media, web links, user profiles, marketing and sales, posts and tweets, roadmaps, and spatial data, and so on. Oftentimes, some of these things that traditionally would have been put into a NoSQL database are actually instead now being stored in things like a data lake, where it's essentially a large storage system, and then various sorts of technologies are involved in accessing it from that medium. Moving into 24.1, which is the introduction of NoSQL systems. Bigtable was kind of one of the first ones to start this. It was Google's proprietary NoSQL system. It was very much of a column-oriented or wide column store. Did very well for accessing things with lots of columns. DynamoDB was a key value, or is a key value data store. Cassandra was created by Facebook. It used the concepts of both key value and column-based approaches. MongoDB and CouchDB are both document stores. Neo4j and GraphBase are types of a graph database, and that's a mathematical graph of nodes and edges stored in a way so that you can do interesting analytics on it. OrientDB combines several of these concepts, and then there's database system classified on the object model approach, or there's some that are native XML or JSON type approaches. NoSQL characteristics related to distributed databases and distributed systems include things like scalability, availability, replication, eventual consistency, replication models, master-slave, master-master, sharding of files across the clusters, and high-performance data access. Many of these things, including eventual consistency, have made their way into both traditional relational database systems and also a new breed of things called NewSQL, which are a mixture of the best of NoSQL technologies with traditional relational data stores. NoSQL characteristics related to data models and query languages. Schemas are not necessarily required, although there is sort of a implicit one that you must know in order to use the data. The data is evaluated, or a schema, if it exists, is evaluated on read, not on create or write. Generally speaking, the query languages aren't quite as robust. Performance could be problematic depending upon what's going on, but typically speaking, NoSQL and big data systems in general are utilized because traditional relational database systems aren't going to work. There is typically some form of versioning and support for things such as schema evolution, where what a schema is changes over time. There are various categories of NoSQL systems. We've talked about them briefly. There are document-based or document-oriented NoSQL systems, NoSQL key value stores, which is basically a name value pair that's stored, column-based or wide column NoSQL database systems, graph-based systems, hybrid NoSQL systems, object database systems, and XML databases. The various levels of consistency among replicated data items, enforcing serializability, the strongest form of consistency. There's high overhead, however, it can be reduced through read-write performance, operation performance. The CAP theorem states that basically you have a trade-off between consistency, availability, and partition tolerance. You may be able to give up one of those for a short period of time. Not possible to guarantee all three simultaneously. Generally speaking, though, it's a trade-off, and it's kind of an interesting theory because you don't really have control over some of those. Partition tolerance basically means a link inside of the network goes down, so there's an isolated element of a distributed system. That can only work for so long. When it comes back online, the idea is that you end up being consistent eventually, or you stop working. And the idea here is that it's about distributed systems without necessarily doing data replication. Designers can choose two of the three to guarantee weaker consistency level is often acceptable in NoSQL distributed systems. And that's what I just said. CAP theorem implies that basically you can pick two out of the three, but you don't necessarily get to truly pick two of the three. Some of them are required. You need to be able to handle partitioning. You don't have a choice. So, and you need to have things available. So, I mean, it's an interesting argument, but it's got to be viewed from a temporal perspective. Guaranteeing availability and partition tolerance is more important. To facilitate this, eventual consistency is often adopted. Document stores are a collection of similar databases or documents. Individual documents resemble complex objects or XML documents. Documents are self-describing and can have different data elements. The basic idea is that a document is whatever the application that reads it and writes it needs in order to do its thing. They typically are very much the opposite end of the spectrum of a column-oriented database, where it's a particular row is essentially a document. Documents can be specified in various formats. They include things like JSON, XML, Parquet, various other types of formats. MongoDB is one of the more common ones. It certainly was one of the early ones. It supports a variation of JSON called Bison, which is a binary form of JSON for performance reasons. Individual documents are stored in a collection, and an example command is first parameter specifies the name of the collection. The collection option includes the limits on size and number of documents. So you have db.create collections, something called project, and it's capped at true. The size is some number, and the max is 500. Each document is a collection that has a unique object ID called ID. A collection does not have a schema. The structure of the data fields in the document chosen based upon how the documents will be accessed. So the reader of the document determines the schema, not something that's native to it itself. Users can normalize or denormalize the design. Document creation is based by using an insert command. You insert a document into the collection. Document deletion is used using the remove operation to remove the document from the collection. So in that regard, you can think of a collection of being similar to a table, and a document being something similar to a row in a table from a relational perspective. It's a little more complex than that because they don't necessarily have to be the same structure or schema, but it's that kind of concept. Figure 24.1 is an example of a simple document in MongoDB. And you can see it's, in this case, it's basically a JSON document that's showing you the ID is P1 for both items, and the other is variations on how things are being stored inside of the document array. 24.1 is an example of a simple document as well. This is more normalized in C, and D is inserting the documents into the collection. MongoDB distributed systems characteristics. It typically uses something like a two-phase commit used to ensure atomic and consistent multi-document transactions. The idea is that a document unto itself is inherently transactional, right? So it is atomic by itself. But what if you have two documents that go together? That's where you have to do something like a two-phase commit. Replication in MongoDB is the concept of a replica set to create multiple copies of on different nodes. It's a variation on the master-slave approach, primary copy, secondary copy, and arbiter. Arbiter participates in elections to select a new primary if needed. Replication in MongoDB, all write operations applied to the primary copy and propagated to the secondaries. Users can choose to read, read performance. Read requests can be processed at any replica. Sharding in MongoDB is horizontal partitioning, divides the documents into disjoint partitions or shards. This allows adding more nodes as needed. Shards are stored on different nodes to achieve load balancing. Important to understand, though, that when you're doing sharding, you're doing so based upon some field. That means that you need to consider that field very carefully so that you can then find which shard something belongs on based upon it later on. It also means that if you want to be able to enable multiple shards and increase them over time, you have to consider that in your key selection as well. Partition field, that's the shard key, which is what I just talked about, must exist in every document in the collection, and it must have an index. Range partitioning is whenever you use chunks based upon a range of key values. This works best in range queries. Hash partitioning is partitioning based on the hash value of each shard key. When we talk about no SQL key value stores, a key value store focuses on high performance availability and scalability, can store structured, unstructured, or semi-structured data. A key is a unique identifier that's associated with a data item used for fast retrieval. The data item itself can be a string or an array of bytes. The application that's reading that array of bytes or string does the interpretation of the structure. There is no query language. DynamoDB is a part of Amazon's Web Services SDK platform. It's a proprietary database approach. The table holds a collection of self-describing items. The item consists of attribute value pairs. Attribute values can be a single or multi-valued. Primary keys can be used to locate items within a table, and they can be singular attributes or a pair of attributes. Volademort is an open source key value system similar to DynamoDB. This is something that's kind of faded from use. You're not going to find this out there in use very often. It's a simple basic put, get, and delete, has a high level of formatted data values or high level formatted data values, consistency hashing for distributed pairs, consistency and versioning, concurrent writes are allowed, and each write associated with a vector clock. Figure 2.4 or 24.2 is an example of a consistent hashing approach. The basic idea is that you should always get a reasonable distribution of your hash function so that your load is reasonably evenly distributed across your stores. Examples of other key value stores: Oracle has a key value store, Oracle NoSQL database. Redis key value stores is basically a cache and store. It caches data in main memory to improve performance, offers master-slave replication and high availability, offers persistence by backing up the cache to disk. This is utilized a lot in web applications, and the idea being that you retrieve something from a cache so that it's much faster. Apache Cassandra, this is still around and still used, offers features from several NoSQL categories. It's used by Facebook and many others. 24.5 is around column-based or wide column NoSQL systems. Bigtable was kind of the first one and kind of kicked off this whole approach. It's a distributed storage system for big data. It's used in Gmail, Google File System for data storage and uses Google File System for data storage and distribution. Apache HBase is a similar open source system, uses HDFS for the data storage, which is the open source implementation of something very similar to DFS or GFS. It can be used in Amazon's S3, lots of other places as well. The HBase data model and versioning, there's data organizational concepts. You have a namespace, a table, column families, column qualifiers, columns, rows, and then data cells. The data itself is self-describing. HBase stores multiple versions of data items. There's a timestamp associated with each version. Each row in a table has a unique row key. The table associated with one or more column families. Column qualifiers can be dynamically specified as new table rows are created and inserted. Namespace is a collection of tables. Cells hold the basic data items. This is an example from HBase. Notice that we're creating an employee that has name, address, and details. We're inserting name, row 1, and we're saying what its name is. It's first name, last name, nickname, job details, and engineer, and so on. And then some basic CRUD operations, create table, column, store, and so on, or column family, and then so on, and then put some data in with a put command where you insert, you scan for something, and then you retrieve something. HBase CRUD operations provides only low-level CRUD operations, create, read, update, and delete. Application programs implement more complex operations. It creates a new table and specifies one or more column families associated with the table. Put inserts new data or a new version of the data into an existing data item. Get retrieves data associated with a single row, and scan retrieves all the rows. Each HBase table is divided into several regions. Each region holds a single range of the row keys in the table. Row keys must be lexicographically ordered. Each region has several stores. Column families are assigned to stores. Regions assigned to region servers for storage, and master slave responsible for monitoring the region servers. HBase uses Apache Zookeeper and HDFS. Graph databases store data as a representation of nodes and arcs. You have nodes, which are vertices, and edges, which connect those nodes. It's possible to store data associated with both individual nodes and with individual edges. That's kind of one of the compelling arguments of a graph database, is that you can have as many attributes on your edges as you have on your nodes, if not more so. Neo4j is an open source system. It uses the concept of nodes and relationships. Nodes can have labels. There are 0 or more. Both nodes and relationships can have properties. Each relationship has a start, end, and end node, and a relationship type. That means that they are directed arcs, so you need to have 2 of them if it's a bidirectional relationship. Properties specified using a map pattern, and it's somewhat similar to ER or EER concepts. Creating a node in Neo4j, use a create command. It's part of a high-level declarative query language called Cypher. Node labels, and there's also variations of this. There's also Gremlin, which is not necessarily for Neo4j, but it's the same sort of concept. Node labels can be specified when the node is created. Properties are enclosed in curly brackets. Here's an example of creating some nodes and some relationships. This is the example of it creating some relationships between the nodes that were created on the previous slide. Note that there's an attribute on some of these, like hours, which is a property of the works on relationship. A path is a way of traversing part of the graph. It's typically used as part of a query to specify some pattern. Schema is optional in Neo4j, and indexing and node identifiers users can create for the collection of nodes that have a particular label. 1 or more properties can be indexed. It's important to note too that Neo4j is basically unlimited in size in a big data sort of world. It can have any number of nodes and edges. The Cypher query language of Neo4j, it's a query made up of clauses. The results of one clause can be used as the input for a next clause in the query. This is a basic query where you basically say match some pattern, and then you can say with some specification where there's specify the condition of the data to be retrieved, and then return, which is essentially your projection of what it is you want to get back out, ordering it in a certain fashion by the order by, and limiting to the number of records that you want or nodes or edges, depending on what you're querying for, to retrieve. And so on. So you can create nodes with the create relationships similarly, but you have to search kind of for the nodes first, and then you do you can remove both nodes or relations. You can set properties after the fact, and you can remove properties or labels after the fact as well. Here's an example query in Cypher. Very cool language to work with. A little weird when you first start out, but very compelling over time. There's an enterprise edition versus a community edition. The enterprise edition supports caching, clustering of data, and locking. That's what you're going to use if you're going to be running this thing with any size. The community edition's pretty much for educational purposes or for small users. The graph visualization interface, subsets of nodes and edges in the database can be displayed graphically. It uses to visualize query results, and it also can update and drag around depending upon, so you can do essentially data exploration in a simple way. Does support master-slave replication. There is caching and logical logs. In summary, we've talked a lot about NoSQL systems, focusing primarily on storage of big data. General categories that we've talked about include document databases, key value stores, column databases, graph databases, and some of the approaches that span across multiple categories. We talked a bit about consistency, and we discussed the CAP theorem. And with that, if you have any questions, do let me know. That's what I'm here for. Stay safe, and we will speak again in the future.